The thing I would like to discuss in this presentation is, of course, it has to do with technosignatures, and in particular with what I called the demographics of technosignatures, which is basically trying to understand what can we say about lifetimes, abundance, and detectability of technosignatures and how they influence each other. So how the chances of detecting technosignatures depends on their demographics. And first of all, let me just clarify what I will mean by detectability in the remaining of this in the rest of this talk. By detectability, I just mean a simple, very simple, basic requirement, which is that if we have to detect a technosignature, this technosignature has to be in our path light cone, meaning that the signal that we receive has to be in causal contact with us. And that is exemplified by a very simple mathematical relation, which you see in this slide, where Ti is the appearance of technosignature and tau is the duration of technosignature. And if this technosignature is at a distance r from us, of course, we can only detect it if the travel time of the technosignature is compatible with being in our path light cone. So I will not enter into any detail about signal strength, observational limitations, instrumental techniques, or what kind of technosignature we have to do with. I'm just using this very, very basic requirement. And this is essentially to simplify things, but also because we don't know much about which technosignatures we are detecting. So I want to keep things as agnostic as possible. Okay, so this is the first definition. And of course, already starting from this very basic definition, we can see that because the galaxy is small compared to its age, meaning that it only takes 10 to the 5th years, roughly, for light to go from one side of the galaxy to the other side of the galaxy, and the galaxy is very old, it's roughly 10 billion years old, any signal that is emitted by any location within the galaxy will cover the entire distance of the galaxy very fast, or again, in a very short time compared to the age of the galaxy. And this implies, by using the causal constraint for detectability, which I showed earlier, this implies that if any technosignature ceased to be active before 10 to the 5th years ago, we cannot detect it now because its signal reached us in the past and went away, and we cannot detect it anymore. So if you think about technosignatures as any other astronomical source, you see that there must be, on one side, the rate of production of this technosignature, and on the other side, there must be a typical duration of these technosignatures, which of course we don't know, but the point is we can only observe those that are in our path light cone. And another implication of that is that if we push the time of appearance of any technosignature back in time, this technosignature has to remain active for a very long time in order for us to catch it. So suppose the technosignature started a billion years ago, it has to be active roughly for 1 billion years. Otherwise, we will not catch it now, okay? Because the time travel is so short. So the farther back in the past the time of appearance, the longer the duration of the signal must be. And this, of course, is telling us already that there is a strong bias in favor of long duration technosignatures if we want to observe them, or if we require that they are detectable from our location. And so if you have a random distribution of technosignatures over the history of the galaxy, most of them probably are long gone, and the ones that you can detect now must either have extremely long durations or have to be appeared almost simultaneously with us, almost coeval with our time of appearance. So this is a very general and very basic requirement. It's probably not so surprising, but I think it's important to state it clearly at the very beginning to be on the same footing. Another thing which is of course, very famous to anyone here is that we can model the number of active technosignature using the Drake equation, but I think it's also interesting to look at the Drake equation in a slightly different way than is usually presented. Usually it is presented in terms of some probabilistic factors, but I think it's also illuminating to look at it in terms of two temporal scales. One is the rate of appearance, which is basically all those factors there, which are, as we know, basically mostly unknown, except perhaps for the astrophysical factors. And so these factors give us the rate of appearance. They tell us what is the frequency of appearance of technosignatures in the galaxy. And the other factor is the longevity, the duration. Okay, and longevity is a term which actually in this context means simply the duration of technosignature, not the longevity of civilizations, not the longevity of a species, but how long their technosignature persists. And if you look at the Drake equation in this way, you see that it's essentially identical to a very generic law, which is called Little's law, which tell us what is the average numbers of items in a system, and you simply have to multiply their average arrival rate, in the system by the average time spent in the system. So if you want to know how many people are in queue for some service, and you know how many people arrive per time interval, and you know how long they stay in the queue, you know roughly how many people will be in the queue. Okay, so this is a very general, basic result, and you can apply to technosignatures, and this is what I mean by demographics. The demographics of technosignatures means that essentially you can treat them as any other population. Okay, so if, for example, you have population of the people living on Earth, or in general, or of any kind of population, and you have a birth rate and a death rate, you can estimate what is the total population. And you see that basically, depending on the birth rate and death rate, you have different behaviors. So, for example, in this example here, which is real data for demography of population on the Earth, you have an initial birth rate which is very, very high, and then it's after a while it declines and it gets more stable. And the death rate also is initially very high and then falls more rapidly than the birth rate, and so on. And so you have different behaviors. And this is something that we would like to do for technosignatures as well. Unfortunately, what is missing here is the data, because we don't know actually what is the birth rate and death rate of technosignatures. But it's clear that that knowing that will affect profoundly the chances that we can detect them. And we did some simulations some years ago, being totally agnostic about the demographics of technosignatures. And what we did was simply to take a random distribution of technosignatures, having random durations and having random time of appearance. And we played around with different distributions. And what we got was essentially that if you only impose this detectability constraint, so the fact that they have to be in our past light cone, and you introduce a selection effect. You only pick up those that are very long-lived, and very long-lived means something which is in excess of hundreds of millions of years. Okay, and this conclusion is robust with respect to the distribution of appearance. You can change the time of appearance with various realistic distribution, Gaussians, uniform, whatever, and you still get that your observations will select preferentially the technosignatures that are long-lived. You can also have you can also pick up some technosignatures which are short-lived, but in this case, as I mentioned before, these technosignatures had to appear very recently, so they have to be almost precisely synchronized with our existence here on the Earth. So whether this is plausible or not, we don't know. But the main result, which is again is very robust and very independent, essentially from the overall assumption, is that one tends to prefer and preferentially detect long-lived technosignatures. Of course, we can also ask a different question based on this simulation, which is now how many technosignatures do we need in the galaxy in order to have at least one detectable today? And this depends a lot on the duration, because if you have short-lived technosignatures, then you have to have a number which is huge. It's almost the same as the total number of stars in the volume in the history of the galaxy. And if you have long-lived technosignatures, interestingly, you can also have very few of them. If you have very few long-lived technosignatures exceeding some hundreds of millions of years of duration, then they don't need to be in a huge number. But unfortunately, I mean, if they are few and they are spread over the entire volume of the galaxy, they will be difficult to actually find. It will be difficult to find out them. Okay, but this is the kind of exercise that one can do with this kind of demographics. And the other question one may ask is the set of detectable technosignature empty? Meaning, are there any that respond to this causal constraint based on these two temporal scales that I was mentioning? Of course, we have no answer to that because we don't have a model of exocivilizations or technosignatures, so we don't know how to answer that. The only thing we can do is to try and do some phenomenological exercise, as I said. So you take, for example, you take those numbers that I showed before, and you see what kind of behavior of mathematical relation have to be fulfilled in order to have a certain number of technosignatures that can be detectable today. And phenomenologically, what one can see is that this number follows a power law with some spectral index. Okay, so the longevity tau of technosignatures to some power will give you the number. And power laws are actually quite frequent in nature. For example, the distribution of city population, of earthquake magnitudes, and so on, or for example, the wealth distribution follows a power law. So there are few, for example, very, very few hugely rich people and a large distribution of not so rich people, and so on. And so you get this kind of behavior very frequently in nature. But unfortunately, we don't know if this applies to technosignatures. And so we can play around with alternatives. And this is another interesting thing. If you look at the death rate, again, this is for people. Okay, so and people are very different from technosignature or technology. But just to give an idea of what you can do, if you look at the death rates, you see that this changes a lot during the age of a person. So as we expect intuitively, people that gets old has a higher death rates, but actually, surprisingly, there is a very high death rates initially, and then it goes down a bit and then goes up again. And also there is a difference between the death rates that depends on the aging of the organism and external causes. So external causes are roughly constant, the rate that causes external causes is roughly constant, while the death rates that depends on aging increases. So you expect that as someone is older, it has a higher chances of dying than someone who is younger. Okay, so this applies in general to people or organisms or biological entities and so on. But what is the expectation for technologies, for artifacts? Okay, in that case, you may have different behaviors, and actually, you can play around again with some mathematics here because there are interesting distributions that you can use where you play around with some parameters, and with some choice of parameters, you get a behavior like the one that I showed before. So where the old is more probable to terminate than the young, which happens in living systems. You can also get something which is similar to what happens with random external causes. So there isn't a clear preference for old or young to die before. But in technology, you have a very interesting feature, which is that the young is actually more probable to terminate than the old. When you adopt a new technology, there is a very high mortality. But when the technology shows that it functions effectively, then you can bet that will probably last very long in the future. And this is called Lindy's law, actually. It's something that has been studied in recent years, where essentially for things that are not living systems, but are more, for example, ideas or technologies, you have a very counterintuitive behavior where you have a short life expectancy when they are new and the long life expectancy when they are old. For example, a book that has been in print for 100 years, you should expect that it will be still in print 100 years from now, and vice versa. Okay, or a technology like the wheel or any other kind of technology that has been very successful in the past will probably live as long in the future as it has been in the past. Okay, so one may wonder if this can be applied to technosignatures. We made a few years ago, we made an attempt in this direction by using this kind of behavior for technosignature, again, adopting different kind of distribution. I won't get too much into the details of that because it is a bit technical, but essentially the idea is you play around with these parameters in the power law and you model different behavior, and you have either a lot of short-lived technosignature or a different distribution where preferentially you have longer lived technosignatures and so on. And you can play around with this thing. Again, as I said, it's a bit technical, but essentially what we found was that by modeling, by playing around with these parameters, we showed that if you have one specific spectral behavior, so if you have a power law which is reproducing this Lindy's law behavior, then you still need a very large number of technosignatures over the history of the galaxy. And essentially, it has to be so large that you should expect, in order to have some chances of detecting them, to have a constant rate of about one techno-emission per year, which seems a very large rate. Of course, I mean, we don't know if it's plausible or not, but this is what you get from simulations. If you get a rate of appearance that is not constant, so for example, you choose a log uniform behavior, in this case, still 20% of all the techno-emissions have to be produced in the last 100 years to have a chance to detect them. Okay, so it's a difficult thing to say whether this is realistic or not. How can one get some insight on this? Well, one thing is we can play around not just with mathematics, but also introducing some physical reasoning in this enterprise. We can, for example, use planetary constraints to see what they can tell us about the probability of having technosignatures of given duration. And one thing that we did a couple of years ago with Adam Frank was to observe that if you look at the oxygen level in the atmosphere of the Earth, and we know that there has been an oxygenation event which happened, started roughly 2 billion years ago, but there was a very large increase in the last 500 million years. And during these last 500 million years, there has been fluctuations in the oxygen level. This is actually from real reconstruction of the oxygen level from real data and chemical models of the atmosphere. And it's interesting because actually, if you want to have fire on a planet, you have to have an oxygen concentration, supposing that the atmosphere is similar to the Earth. You have to have an oxygen concentration which is higher than, say, 16% roughly. So we now are at 21% roughly. And so you have to exceed a certain threshold, which we call the oxygen bottleneck. This oxygen bottleneck is essential if you want to start a fire, but it's not essential to have complex life. So in principle, you could have complex life on a planet with enough oxygen in the atmosphere, but this complex life will never have access to energy from combustion, which is arguably probably the simplest thing to do for a newborn civilization. So this is the kind of constraint that one can use maybe in the future to get some insight on whether you can start a technology and a civilization on a planet depending on what are the constraints in the chemistry of the atmosphere. And another thing one can do is playing around with energy, because we know from Kardashev's pioneeristic work that you can classify civilization and technological levels in terms of energy consumption. And we know that Kardashev introduced this classification where, based on the energy consumption, you have a ladder of technological advancement, so to speak. And the point is that at more or less at the same time that Kardashev was doing this classification scheme, someone else pointed out that actually you cannot do this without any constraint, because you every time you produce energy or you transform energy, you get some waste heat, and this waste heat will introduce an additional source of heat in a planetary environment, which is in addition to the radiation that you receive from the star. And so, and this calculation already in 1961 showed that if you keep growing with energy consumption at the present rate, you will have a very short time to do this in a planetary environment, just because of this very basic constraint that comes from the second law of thermodynamics. It's not, some fancy thing. It's really elementary physics. And we, a couple of years ago, did a similar calculation by introducing this energy balance and introducing this additional heat coming from energy conversion. And in fact, it's true that if you keep growing at an exponential rate, so with the same level of power production that we have been having for the past 50 years or so, and you keep growing, in principle you reach very easily in a short time, you reach a Kardashev 2 level. But at the same time, you are heating the planet so much that essentially you will not be able to reach this level by remaining on the planetary surface, because the planetary surface will very rapidly, in a time scale which is less than 1,000 years, will become uninhabitable. Okay, so there is a very short habitability lifespan if you keep growing at the same rate. We did this with various stars using the habitable zone estimation and modifying them by introducing these additional terms. And essentially, if you remain on the planetary surface, you will never reach the Kardashev level, because the maximum level you can reach is actually less than 1. You cannot even reach Kardashev. And this is independent by what kind of energy production mechanism you use. It is true even if you just use solar power. So if you want to keep doing that and you want to reach Kardashev level 2, you will probably have to find other solutions or other trajectories. And of course, you can imagine what they can be. One can only classify them very broadly, and we don't know which is more plausible than the other. But one possibility is, as I said, that you keep increasing the energy consumption exponentially, as we've been doing in the past, and then you will exceed planetary limits in a very short time. And this tells that if everybody does like that, you will never have very long-lived technosignatures, probably. You can stabilize energy consumption in some way. I don't know which, but I mean, this is just discussion of scenarios, not giving solutions. And the other possibility is that you expand beyond the planet, and then you use space infrastructure for energy production and technological activity, and so you expand the planetary boundaries and you exceed these planetary limits. All of this, I think, is very important, because if you want to do some realistic model of technosignatures, you probably have to deal with these kind of constraints. You cannot just simply imagine fancy technology without even taking into account the limits that the physics and the chemistry of the planetary environment imposes. So to sum up my presentation, what I want to emphasize is that, first of all, the duration of technosignature is very important. It's crucial for establishing the chances of success in detecting technosignature, and possibly it is the dominant factor. This is probably the most relevant thing to consider. One also has to keep in mind and to realize that even if you have a short-lived civilization, which, for example, lasts only a few thousand years, these can still produce long-lived technosignatures. If you build a megastructure, or if you build a Dyson sphere, for example, that will outlive probably the civilization that produced it. But of course, we don't know if this is plausible. And also, we don't know if you can ever reach that level of technological advancement before you exceed the planetary limits. So we don't have a priori model. We can just explore possibilities and play around with mathematics and with physics and try to see what happens. If you are, of course, if you are a theorist. If you are an experimentalist or an observational astronomer, then you just keep looking and you hope to find something, and then maybe we will explain later on what happens after we have made a detection. But meanwhile, we may get some insights from planetary constraints and this kind of demographics. Okay, thank you.
Thank you very much, Amedeo. So we have some time for questions. And you can just put any questions into our Q&A function within Zoom. There's a question from Caleb Strom. Would this potential sampling bias also apply to physical artifacts, since an artifact could remain detectable irrespective of the lifespan of its creators?
Yeah, I agree. That's what I just mentioned in the conclusions. Yeah, I agree. It is still true, though, that you will detect preferentially these long-lived artifacts. But I agree that duration of artifacts is not the same thing as duration of civilizations, and so you may have a galaxy which has a lot of long-duration artifacts, even if the duration of civilization is short. Yeah, I totally agree.
So you mentioned the theoretical perspective and the kind of observer's view. How do we put those together?
Well, that's really a good question, and I'm not sure I have a clear answer. I think that talking about these things can perhaps give you some insights on what is the most effective observational strategy, because suppose at some point you convince yourself, you can remain totally agnostic, okay? You can say, okay, I will try and observe whatever is out there. But we know that it's not always like that, because you only have a limited time of observation. You have to decide where to point your instruments, what frequency to look at, and what this kind of things, what kind of signal strength, and so on. And so maybe by taking into consideration this information, you can perhaps design a better strategy. So suppose you convince yourself that there is not much hope of detecting short-lived technosignatures like the ones that our civilization is able to produce right now. Then you can focus your effort on detecting only, long-lived technosignatures, for example, beacons or Dyson spheres or megastructures. On the other side, if you think that these are not plausible, then you will focus your observations on some ephemeral, some very short-lived technosignatures because you think that they have a higher chance of being out there. So yeah, I think that is interesting to have these kind of discussions between theoretical people and observation people.
Okay. Question from Daniel Angerhausen. How important is the duration of our searches? Right now, the 50 years we're searching are small in comparison, but what if we looked for 100,000 years?
Yeah, hi Daniel. Yeah, that's also a good question. I think that if you go from 50 years to 100 years, it doesn't make a huge difference in this kind of thing. But it's a good point to raise, and there is a recent, by the way, there is a recent paper by Claudio Grimaldi, which I think he presented in some poster here at this conference, which is very interesting, I think, in this respect, because he shows that already the fact that we haven't detected anything in the last 60 years is giving us some interesting constraints. So if you increase the duration of observations, these constraints will change. I don't expect that they will change too much if you don't change by some order of magnitude, perhaps, or a few order of magnitudes. So yeah.
So further question from Milton Mendoza. Have you thought of looking at species duration from a paleontological perspective as a proxy for civilization duration to add as a different model complementary to Lindy's law?
Yeah, this is actually a good point, and it is something that I have been very interested in recently, and I'm trying to figure out how to do that, and I'm trying to collect data. And one problem is we know quite well what is the distribution of durations of species on the Earth. So we, at least for those species that left some trace in the paleontological record, we can put some very good constraints. One problem is that, as I showed before, is not clear at all, and actually is probably not true that the longevity of organisms and species or biological entities is the same as something more abstract as a civilization, for example, and even less for technologies. So you probably have to model things in different way depending on the class of items that you are dealing with. But yeah, I agree. It's very interesting, and this is something which it's an interesting project which I'm trying to set up and devote some time. So if someone has ideas or want to establish some collaboration, I will be very happy to discuss it. Yeah, I think it's very important.
Okay, Catherine Denning notes, this might be thinking ahead too far, but in archaeology, we find that preservation bias really skews our interpretation of what used to exist. That is, if you only find certain sorts of technosignatures, there's a tendency to assume there wasn't anything else there, but there may have been. In archaeology, the classic is stone tools, which survive over millions of years versus everything else that doesn't preserve. What's your take on that?
Yeah. I agree. This matches what I was telling before, and if we were lucky enough to have some actual data, then we should be aware that there is this selection effect. Right now, we don't have any data, so unfortunately, it's a bit premature. But I think it's a very interesting point, and unfortunately, I also think that for based on these mathematical models, I think that the chances of detecting something which is very similar to our level of technology or the kind of technology that right now we are capable of producing is very small. We have a very small chance of doing that. So I think we are biased towards long-lived artifacts or long-lived technosignatures, and this is something we should take into account. Yes.